Number 2.
Why is it necessary to use the average atomic mass of all isotopes, rather than the mass of the most commonly occurring isotope when referring to the atomic mass of an element? So meaning, when we look at any old atomic mass on the periodic table, why is it important that that number considers all versions of the isotope? Well, elements, with the exception of the most simple atom, which is just hydrogen with one proton and no neutrons, elements rarely occur as only one isotope. Rather, they exist as mixtures. They're mixtures of different isotopes. We've referenced carbon in this course already, hydrogen in this course already, as having 3 different isotopes. Hydrogen 1, hydrogen 2, hydrogen 3. Carbon 12, carbon 13, carbon 14. We have different isotopes of the same element. What we're saying when we say they exist as mixtures of different isotopes in various masses, it means if I get a sample of carbon, it's not as though I might have like a very concentrated chunk of carbon 13 specifically. If there's a certain amount of oxygen in this area, it's not going to be a very concentrated amount of oxygen 17 rather than 18. No, it's completely mixed up. It's completely mixed up. What we tend to see is that if we have the percentage of a naturally occurring isotope, any particular sample is also going to have that same percentage. So we use a weighted atomic average mass. Now this word right here, weighted, is key. For example, we know from using the periodic table that carbon has an average atomic mass of 12.011 grams per mole, or AMU. And we know that carbon has 3 isotopes: carbon 12, carbon 13, and carbon 14. I don't know if any of you have noticed this before, but if you take the sum of all 3 of these numbers, 12 plus 13 plus 14, and then you average them, divide them by 3, you get 13. The average of these 3 numbers right here is 13. So why isn't the average atomic mass, right, the average of all these different masses, why isn't this value 13? Why isn't the value reported on the periodic table 13? Because it's weighted. It turns out that carbon 12 constitutes about 99% of the naturally occurring carbon, and carbon 13, there's about a little bit less than 1%, and then carbon 14, we're looking at an incredibly small percentage. And so because there is so much carbon 12 compared to carbon 13 and 14, and it's weighted, okay, the weight of all this carbon 12 is actually going to make the average dip closer to the 12 mark as opposed to the 13 or the 14. Now, if we saw these percentages different, which we do in other elements, and when we consider the percentages of their isotopes, we see that other elements, maybe this middle isotope is more like 20%, and so we see this average creep up. With this example, it'd be creep up closer towards 13, right? But that's in other elements with other isotopes. For carbon, because there's so much carbon 12, that average is very close to 12.